All right, so the plan for today is to start chapter 3, particularly 3.1 and 3.2. So 3.1, just introducing the idea of having a problem-solving strategy. Chapter 3 is about application problems, or what we might call word problems, and that's a topic that some folks kind of struggle with a little more than other topics. So since folks tend to struggle with that, can we lay out a strategy? Can we lay out a set of steps that we can follow and maybe serve as kind of a guide for us to get through that problem? And then 3.2 on solving percent applications. We'll probably just get through talking about solving a couple of percent problems today, and then we might wrap up 3.2 next time. The quote of the day for today is from the Roman lyric poet Horace, from his work Satires. There is a mean in all things, and this is a rough translation of the Latin. There is a mean in all things, too far to the right or left of which good cannot be found. So I think a good quote for life, for academic life, but also just life in general. I'll just leave it there since we spent a good bit of time discussing some study strategies and so on. So we'll get into the chapter 3 material. So from the book, from 3.1, we have these 7 steps, which I just realized kind of copied over a little funny. So step one, read the problem. So we want to just slow down a little bit. If we see a word problem, we might get a little flustered. We might say, oh, word problems are tough or whatever, but just first read through the problem. Just get an idea of what's going on. 2/3 of the children in a 4th grade class are girls. Okay, so we have children overall, we have girls. If there are 12 girls, what's the number of children in the class? So identify what we're looking for. Well, what are we looking for? Number of children in the class. That's what we're being asked. That's the question part. What is the total number of children in the class? Name what we're looking for. In other words, assign a variable, assign a letter. We might use X just kind of as a default, but if we're looking for number of children in a class, maybe we use N, or maybe we use C, or right, you could use whatever variable you like, but choose a variable and note what it represents. Translate into an equation. So figure out which expressions are being equated here. We should have one mathematical expression equals another mathematical expression. One of those expressions could just be a number. But how do we translate this into an equation? What are the different quantities that we are looking at and that we want to equate to one another? Or perhaps if this was an inequality, that we want to say that one of these quantities is less than the other. And then solve the equation. So this is chapter 2. And then lastly, well, maybe not quite lastly, I guess they're saying answer with a complete sentence, which is a little ironic because in WebAssign, you usually don't have a complete sentence. You usually just type in the number, but essentially, lastly, does the answer make sense? So there's this idea, somebody wrote, I think, a book or a little like PDF kind of thing. And I think it was like an MIT professor or somebody from one of these, bigwig colleges, and he called it street math. And the idea was like, these are like the rough and tumble math techniques that you like use on the street, like these are not like the formally correct mathematical techniques to use, but these are things that are, a little bit messy, but actually work pretty well in real life. And one of the ideas of street math is something like check units. So for instance, if we have like distance equals rate times time, we know that distance is in, say, feet, rate is in maybe feet per second, and time is in seconds. Once we go through and we cancel all of the units and all of that, do we get something like feet equals feet? Or do we get a claim like feet equals seconds, which is obviously wrong? I can't say that 6 feet equals 3 seconds. That doesn't make any sense. So that's, one idea in street math. Another idea is just, does it make sense? If I'm looking for number of children in a class and I get -13, does that make sense? Well, probably not. If I'm looking for number of children in a class and I get, 12.7, does that make sense? Probably not, right? I can't have a negative number of kids in a class. I can't have a fractional number of kids in a class. So does my answer actually make sense in the context of what I'm looking at? So on one hand, word problems can be a little more challenging because there are just these couple of extra steps. We have to kind of come up with the equation in the first place. But if we flipped it on its head a little bit, word problems can actually be beneficial because they give us a context to work with. If I go back, say back here, and I ask you, is x equals 17 a reasonable answer to this equation? Well, I don't know. I mean, I have no idea like what this equation represents. There's no context. I have no way to look at my answer and say, is that a reasonable answer? I mean, I got a number, but the solution to an equation can really be any number. But if I'm in a situation like this where I have a word problem, there's almost always a context. And I can ask myself, does my answer fit that context? So I actually get a leg up in word problems. I get context. Sometimes I get units. So feet or seconds or meters or whatever. Sometimes I get units that I can check and compare. Sometimes I get context. I can maybe put a bound on my answer. If I have two extremes, I maybe know that my answer cannot be less than this number or bigger than that number, and that gives me another way to check my answer. So coming up with a creative way or ways to check your answer and see if it fits the context of the problem can actually be a big benefit for having a word problem. You have that context to compare your answer to. And then if you get an answer that doesn't fit that context, hopefully the problem was phrased correctly. And as long as the problem wasn't phrased strangely, then we can go back and we can say, okay, well, my answer doesn't fit the context. Let me double check all of my work. That's an indication that something went wrong. So let's go through these steps for this problem. So again, read the problem. 2/3 of the children in the 4th grade class are girls. So I'm imagining I have a class and I have, some girls and some boys. We have 2/3 of the children in the 4th grade class are girls. So more of the children are girls than boys. So let's change some of these blue circles to black. Okay, so now this isn't a perfect representation. So I have some girls, some boys. But now I know there are 12 girls. If there are 12 girls, what's the total number of children in the class? All right, so identify what we're looking for. We're looking for the number of children in the class. Let's give that a name. The number of children in the class, let's just call it C. We could use X, we could use N, we could use, any letter, or, you could use smiley face to represent number of children in the class if you wanted to. But we'll name it C for children. Okay, so we have a variable representing that. Let's translate that into an equation. So on one hand, the number of girls in the class are 2/3 of all the children. On the other hand, the number of girls in the class are 12. So the girls can be represented by two different algebraic expressions. One of them super simple, just the number 12. The other one is 2/3 of all the children. In other words, 2/3 C. when we see the word of, we usually think multiplication. So if I have half of a gallon of milk, that's like 1/2 times, one gallon jug of milk. Or 2/3 of all the children is 2/3 C. Both of these are representing the same thing, the number of girls in the class. So if I want to translate this into an equation, I have one expression representing the number of girls, another expression representing number of girls. Those should be equal. They're representing the same thing. And the good news is that after we get through steps 1 through 4, well, at this point, and this is something that we say a lot in math, we've reduced the problem to a previously known solution method. I just now have an equation in a variable that I want to solve. I learned how to do that in chapter 2. So at this point, I can forget about the problem, forget about the word problem for the time being. I want to bring it back at the end. But for the time being, I can ignore the fact that there's some word problem in the background. And I can just say, okay, like I have 2/3 C equals 12 that I want to solve for C. I isolate the variable term. Variable term is already isolated. I isolate the variable. Two-thirds divided by 2/3. On the left, they go away and just give me a C. On the right, I have 12, which I'll write as 12 over 1, divided by 2/3. Now I have to simplify. I know if I'm dividing by a fraction, I invert and multiply. I can divide out the 2 with the factor of 2 and the 12, leaving me with 6. And I get C equals 18. That's the solution to my equation. And now let's go back up and bring this back to the word problem, to the application. Does it make sense that there are 18 kids in the class? Sure. If there are 12 girls, I know there's got to be more than 12 total students in the class, right? If I got an answer like 6, I can't have 6 total students in the class, but have 12 girls. So 18 is bigger than 12. It's not like a negative number. It's not a fraction or a decimal or something. It's a sensible answer. Yeah, there could be 18 kids in the class. Is 2/3 of 18 12? Yeah, it is, right? 1/3 of 18 is 6, so 2/3 of 18 is 12. So it does make sense for this to be the solution to this problem. Again, if I had, let's say mistakenly done 12 times 2/3 and canceled this and got the 3 goes into 12 4 times, if I would have mistakenly got something like the number of children is 4 times 2 is 8, when I bring this back to the application, I'd actually see, oh, that's wrong. Let me check my work. And then I might realize that I made a mistake with that fraction simplification. So word problems can actually be a nice benefit because it gives you some context to check against. And then I can answer with the complete sentence. I can say the number of children is 18. Okay, so let's take these steps and go through one more problem, and then we'll work through a couple. I'm going to copy these down. Then we'll work through a couple together. Well, just ignore those 8, 9, 10, 11, whatever. It is just not my day today for getting tech to work out. Okay. Okay, so let's read through the problem, get an idea of what's going on first. The sum of two numbers is 0. So right away, I see something interesting. I have two numbers, not just one number. I'm a little curious as to how this is going to work out. Am I going to need like an X and a Y or something? I'm not sure. But let's read on. One number is 6 less than twice the other. Find the numbers. Okay, so what am I looking for? I'm looking for the numbers, plural. Let's name what we're looking for. Let's call the numbers X and Y. So I choose my variables. I'll call them X and Y for the two numbers that add to 0. Translate into an equation. Now this could be a little bit complicated, right? Because on the one hand, I have the sum of two numbers is 0, which makes me think of something like X plus Y equals 0. On the other hand, I have this other equation that's a little more complicated, that something equals something. So I almost have like two equations here. Is there a way to maybe simplify one of these equations? Is there a way to rethink about this problem in terms of just a single variable? Well, let's focus on this first equation. X plus Y equals 0. Well, if the sum of two numbers is 0, then one just has to be negative of the other, right? So either X equals negative Y or Y equals negative X. So if I come over here, really what I'm looking for, the two numbers that I'm looking for are negative Y and Y. Because they have to sum to 0. So I really see that this criterion, applying this criterion that X plus Y equals 0, you don't see the work. Can anybody else not see like where I wrote X plus Y equals 0 or negative Y comma Y here?
I can see it.
Okay, thanks. Yeah, I'm not sure. So in chat, somebody said, I don't see the work. I'm not sure exactly what you mean by that. Oh, you don't see the screen at all? Um, it does seem like other folks are able to see the screen. Can you, maybe, um, yeah, I'm not sure. Is your Zoom window open or let me just redo the share, see if that fixes it. Yeah, it might be a Zoom issue or it might be an issue with your computer, but it seems like other folks are able to see the window. Okay, but so by applying this equation, we can really see that we just have one variable left to apply our second sentence to. Okay, so one number is 6 less than twice the other. So let's do this in X and Y first. So one number is, when we say is, that word usually means put an equal sign there. 6 less than twice the other. So one number, let's say X, is 6 less than twice the other. Now we might be, if we're reading through this and we're not really careful about the grammar, we might have picked up on something like less than. I thought that meant an inequality. X is less than 3. But less than can also mean subtract, can mean take away. So 6 less than some number If I have $6 less than somebody else has, then I have what they have minus 6. So 6 less than something means something minus 6, right? I like to bring everything back to money if I can, because it's pretty tangible, right? We work with money a lot. We understand that. So if I have $6 less than that person has, I have the amount that they have minus 6. That's the amount of money that I have. And what are we 6 less than? We're 6 less than twice the other variable. In other words, 2y. Or I could say something like, I know that x equals negative y. I could say negative y equals 2y minus 6, applying my previous discovery. So I now have an equation for y. And at this point, I can, in a sense, forget about the word problem. I can just say solve this for the variable y. And again, that bookkeeping is important. It's easy to forget a negative, especially when that negative is at the beginning of a statement like this. So we just want to make sure that we get everything copied down correctly. I want to isolate the variable term. These go away. I want to isolate the variable. Since this is an equation, not an inequality, I don't have to worry about dividing by a negative. Nothing special to do there. Negative 6 over negative 3, a negative over a negative is a positive, and 6 over 3 is 2. So I get y equals 2. Now if I come back up here, y equals 2, and then x, which is negative y, x is going to be negative 2. So now coming back up to my word problem, putting this back into context. For a problem like this, I don't really have a ton of context to work with. I don't have children in a classroom where I had a little more context, but I still have some context. I have two numbers. Is there some 0? Yeah, it does seem like it is. Is one of these numbers 6 less than twice the other? Well, if I double 2, I get 4. Is negative 2 6 less than 4? Yeah, that also seems correct. So I can check my answer. And then these are my two numbers, x equals negative 2, y equals 2. And I could, I suppose, write in a sentence, the numbers are negative 2 and positive 2. So the challenge in this one was that I had a couple pieces of information, and I had to really synthesize one of those pieces of information and then leverage what I learned from that to make my second piece of information solvable, right? And just as an aside, there are other ways that I could have approached this. Or maybe that I could have thought about it. I mean, you're going to get the same answer either way. But another way that I could have thought about this is I generated this equation. I generated this equation. This variable x now has two different representations. One as negative y, one as 2y minus 6. Since negative y and 2y minus 6 are just different representations of the same thing, I could equate them. I get the same equation, just a slightly different way to think about it, right? So that's the other thing about word problems, is there can be more than one way to think about such a problem, to set it up, more than one way to solve it. You should get the same answer at the end, but there might be a few different paths to that answer. That might seem a bit strange, but remember, even back in something like basic equation solving, we could choose to put the variable terms on the left or on the right. Different people could choose different sides to put them on. It's not that one is right or one is wrong. We get the same answer at the end, but different people might choose differently. Okay, so let's jump over here then. And we have two similar problems to the ones we just did. So let's take some time to work through these. I think we'll take maybe, say, 3 minutes to work through the first problem. And then we'll come back and work on the second. And as always, if you get through the first problem a little quicker than, say, 3 minutes, then you can start working on the second. You can start working ahead if you want to. But we'll take 3 minutes, work on this first one, come back and talk about it. Okay, so let's go through the steps. Again, if you didn't quite make it through, that's not a big deal. If you made it through and started on the next one, great. But don't worry if you didn't make it all the way through. So first, read the problem. 1/4 of the candies in a bag are red. If there are 17 red candies, how many candies are in the bag? What are we looking for? We're looking for the number of candies. So let's also call this C, just kind of incidentally. Children and candies start with the same letter. So we'll start with C for the variable. So that's the name we gave to what we're looking for. And again, now I want to translate into an equation. An equation is a statement that two expressions are the same. So what is the kind of common element here? What is, in a sense, like the key that I can use to match up two different pieces? Well, red candies. I have two different ways of making a statement about how many red candies there are. One way is the simple statement that there are 17 red candies. That's one expression. Another way of saying how many red candies there are is that it's 1/4 of all the candies in a bag, or 1/4 of or times C. So the number of red candies is both 1/4 of the total number of candies, 1/4 C, and also 17. But these are clearly the same thing. These are just the number of red candies stated in different ways. So 1/4 C equals 17 is what I get when I translate into an equation. Solve the equation. So at this point, we can really forget about the fact that we're dealing with a word problem. We can just go through our equation solving steps. We isolate the variable term. Well, that's already done. We isolate the variable. Divide both sides by 1/4. On the left, I just get C. And on the right, I get, and again, I have to be careful here, right? If I was a little sloppy with my arithmetic, I might think something like 17/4. But then I check my answer and I say, well, can I have the number of candies be 17/4? That doesn't really make sense, right? Oh, okay, I made a mistake. I need to be a little bit more careful with my arithmetic. I'm dividing by the fraction, so I need to invert and multiply. And 17 times 4, well, that's 40 plus 28 is 68. Saying that there are 68 candies, that makes a lot more sense. 17/4 candies is kind of, that doesn't make sense with the context. But 68 candies does make sense. If 1/4 of all the candies is red and I have 17 red candies, I should have more than 17 candies to start with, of course. That's good. 68 is bigger than 17. And is 1/4 of 68 17? Yeah, it is. So I've checked against the context of the word problem that this actually makes sense, and it does. Right? Again, if I was just solving an equation, if I just gave you 1/4 C equals 17 and just said solve this for C, if you ended up with 17/4, I mean, that could very well be a good answer to just some equation. But the context can be really helpful. And I really want to stress that, because a lot of people look at word problems and they think word problems are terrible, or they're more complicated. And there's a sense in which they're more complicated because you have to set up the equation first. But again, there's also a sense in which they can be really helpful, and we can view this as a positive because we have so much more context that we can check an answer against and see if it's a reasonable answer. I ought not get a negative number of candies or a fractional number of candies, or 68.2 candies. That wouldn't make sense with the context. It gives me a lot more to work with having this context. I've checked, and now I can answer, there are 68 candies in the bag. Suppose I should put a period if it's a sentence. Okay, so we have a question that's similar to our second one that we did previously. Let's take about 4 or 5 minutes to work through this one. It's a little longer. There's a couple extra steps. And you might go down a path and realize maybe that doesn't seem very fruitful and have to back up and try a different path. So maybe 4 or 5 minutes for this one. Okay, let's come back and work through this one. So like usual, I kind of started working through it during that time so that if you were stuck at a certain point, maybe this gave you an idea, uh, a way to get unstuck. So first read the problem. The sum of two numbers is negative 63. Again, we see this two numbers. That's a little different than what we saw last time. One number is 33 more than the other. Find the numbers. What are we looking for? We're looking for the two numbers, right? Find the numbers. Name what we're looking for. We'll call it X and Y. So X is one number, Y is the other number, and translate into an equation. And similar to last time, we have two different statements. The sum of two numbers is negative 63. The sum, meaning add them together, X plus Y, is equals negative 63. So this is my first equation that I have. My second statement, one number is 33 more than the other. So again, that is connecting two quantities with an equal sign. One number, let's say X. If you had picked Y as the one number, it wouldn't have mattered. You'd have just got, your Y, the number you get for Y would be the number I get for X and vice versa. Since we just want to find the numbers, we just artificially made X and Y. It doesn't matter if, your X is 1 and your Y is 2 and my X is 2 and my Y is 1. That doesn't matter as long as the two numbers are overall the same. So I chose to call my one number X equals 33 more than the other. I wrote this as Y plus 33 because I think that makes a little more sense. If I said 33 less than the other, I'd want Y minus 33. So I'm kind of keeping that same context. Or in other words, if I have $33 more than this other person, I have what they have plus 33. So that's how I usually think about this. It seems a little backwards because we kind of flip-flop things, but just being really careful with that grammar, really careful with the meaning of all these words, and making sure that we've got everything. So 33 more than the other number, X is 33 more than Y, X is Y plus 33. Now I have two equations with two variables. I see that my one equation tells me something about X. It says that X is this. If I can solve my other equation for X, then I'll just have two statements about the same thing. In other words, if I see that by subtracting Y from both sides in the X plus Y equals negative 63 equation, I get X equals negative Y minus 63. Well, now I have this thing X on one hand is equal to Y plus 33. On the other hand, that same thing, X, is equal to negative Y minus 63. Therefore, negative Y minus 63 has to equal Y plus 33 because they're both just representations of the same thing, namely X. So we've got through step 4 now. And now we just have to solve the equation. So for this step, I can kind of forget that I'm working on a word problem here. I just go back to chapter 2. If I just said solve this equation for Y, what would I do? I would isolate the variable term, say by adding Y to both sides. That puts my variable term on the right. So then I want to get rid of my constant on the right and move it to the left. Minus Y plus Y, they go away. 33 minus 33, they go away. Y plus Y is 2Y equals, and what is that? It's going to be 96 with a negative. Or I get Y equals negative 96 over 2, or Y equals, well, 100 over 2 will be 50. So if I go down to 48, I think that gives me the right number, and then I make it negative. Again, in a problem like this, I don't have a ton of context. I'm not counting number of children or number of candies or something. So maybe negative 48 is a fine answer. So if I have y equals negative 48, what is x then? Well, we can get x. It's a little more complicated than the last example, but I could get x, for instance, by taking y and adding 33 using this second relationship here between x and y. Or I can say that x would be negative 48 plus 33. Or what's that going to be? Well, if I start at negative 48 on the left side of 0, and then I move to the right 33, this is going to be negative of, well, I can think of it as negative 1 times 48 minus 33. That's another way that I can think about it. I can think about it starting to the left and moving to the right, or thinking that I have this distributive property. I could think that negative 48 plus 33, I could have gotten that by distributing a negative 1 factor into 48 minus 33. And here I see that this is 40 minus 30 is 10, 8 minus 3 is 5, negative 15. Essentially, by construction, x is 33 more than y, so this should be correct. Is it true that these two numbers add to negative 63? Negative 48 plus negative 15 indeed gives me negative 63. So I've checked my answer. I've made sure that all of the components of the original word problem are satisfied. I checked against the original word problem, not just the equation that I got, because I want to make sure that these actually satisfy the original word problem, and I didn't make a mistake at any point in this the problem solving strategy. And then I suppose I could go through and say the two numbers are negative 48 and negative 15. Are there any questions on 3.1? Any questions on either of these two problems or on this topic? Okay. So moving on to 3.2, we might not get through all of 3.2 today, but solving percent applications. Oh, somehow I lost one of my, oh, here. I told you that today was just not a good tech day to me, and today was not a good tech day for me, and that's continuing on. So there we go. Solving percent applications. So we're looking at applications that involve percents in some way. And we have three basic types of percent problems. Maybe I'll give myself a little more space here. We have three different basic types. What percent of a number is another number? What number is p% of another number? Or the number a is p% of what number? So let's, for each of these in general, before we move on to specific examples, let's kind of work through these first four steps, read through these questions, read through these basically word problems, identify the variable, and set up an equation. So what percent of A is B? So the thing that we're looking for is P, and we're thinking of P as kind of a percentage. We'll just represent it as P. I'm not going to write P%. I'll just write it as P, but we'd think when we get an answer, if we got P equals 0.15, we change that to 15%. So what percent of A is B? So one way to think about when we have an abstract question like this is to pick an easy problem. So I know that, for instance, 50% of, let's say, 10 is 5. So how could I arrange these numbers? 50% of 10 is 5. How could I arrange those into an equation? Well, I kind of notice maybe that 50% times 10, or 0.5 times 10, does equal 5. I could also have, so I can go from a general question down to a specific case to kind of help me get a little bit of a bite on the problem, help me get somewhere to get started. Or I could use my more general techniques, things like, okay, when I see of, that usually means times. And when I see is, that usually means equals. But either way, I see that P times A equals B. And we're looking to solve this for P. And I actually can already find the general solution. P equals B divided by A. So these percent problems, if you're not careful, it's easy to get things backwards. But if you're careful, if you go through methodically and carefully, and especially if you look at special cases like this, 50% of 10 is 5, especially if you go through and check with kind of a special case and say, does that make sense that I wrote it this way? I think they're not too bad. Okay, now we're asking what number is P% of A? This is actually maybe the easiest percent problem. Well, since we're looking for a number instead of a percent, maybe I'll call this X. And what number is P% of A? Let's again say what number is 50% of 10, and this should be the number 5. But again, I see is and of kind of cluing me into an equal sign and maybe a multiplication. I think this is going to be X equals P times A. Does that make sense with my special case? Is 5 50% of 10? Does 5 equal 0.5 times 10? Yeah, it does. So I want to solve for X. But I mean, it's already solved for X. I just need to simplify the right-hand side. So this is maybe the easiest of the three in the sense that once I construct the equation, I'm basically done. I just have to simplify, and then I have the answer. I don't need to do any equation solving steps. And then the third type, the number A is P% of what number? What am I looking for? The thing that says what number? Let's call that X. I see is cluing me into an equal sign. So A is P% of X, P times X. So again, for instance, 5 is 50% of 10, and 10 would be the number we're looking for. I'm looking to solve this for X. And so I can divide both sides by p and get x equals a divided by p. This might be the hardest one to check with a special case, but let's work through it. Is it true that 10 equals, and again, I'm just picking the special case as a way to check myself, right? I want to solve something in general. I know an easy special case. I think I have a general solution. Let me check with my special case. Is it true that 10 equals 5 over 50%? Or is it true that 10 equals 5 over, well, I know 50% is just 1/2. And if I have a fraction in the denominator, I invert and multiply. 5 times 2 is indeed 10. So this does mesh with that special case I chose. When I'm choosing a special case, I want to choose one that's fairly easy. I don't want like, whatever 300 is, or let's say 375 is 37.5% of 1,000 or something, right? I don't want to choose like crazy numbers, but I also don't want to choose something super easy that like is 100% of 1 or something, right? Like that's a little bit too simple to act as a good check. So there is a little bit of artistry in choosing a good special case to check. You want it to be not too complicated, but not so trivial that it doesn't really act as a good check. Or like I wouldn't want to, say 0 is 0% of 1 or something and use that as a check. That's going to be kind of an annoying one to try to check. But I see that, this does seem correct with my special case. And when I went through and carefully, pulled out the meaningful mathematical expressions, the is, the of, and so on. Okay, so let's do this for specific, let's work through this process for specific problems. So first, what number is 7.5% of $330? So maybe we're trying to find, say, sales tax on an item that is $330 and sales tax in our area is, let's say, 7.5%. So identify what I'm looking for. I'm looking for the thing, what number? Give it a name. I'll call it X. Again, I notice is and of. So X is 7.5% of times $330. For my purposes, I won't explicitly write the dollar sign, but I'll just kind of remind myself at the end that everything's in units of dollars. I'll put that dollar sign back in at the end. I typically leave my units off during the calculation. If I really want to check my units during a calculation, if I have, like feet and feet per second and seconds and things, if I want to check them all, I might write them below and kind of check my units that way. But I find that if I write my units in the same line as all of my arithmetic and all of my algebra, I tend to just be a little bit more likely to get these to get things messed up, right? To misinterpret this or see it as a number or something like that. Okay, so this is in a sense the easiest of the three, right? I mean, I want to solve this for X, but I already have the variable isolated. It's already solved for X. So really, I just need to simplify here. So the crux of this problem, the most difficult part, was taking the words and translating it into an equation. I didn't really need to do any equation solving steps. I just need to simplify. Now, 7.5%, this percent wants to move the decimal place, the decimal 2 places to the left. I only have one place that's visible, but of course, 7.5 is the same as 07.5, right? 7 units and 5 tenths is the same as 0 tens, 7 units and 5 tenths. And now I can move the decimal 2 to the left and get rid of the percent. In other words, this is 0.075 times 330. And for, I think, the first time in the course, we are going to jump over to the calculator. So we don't want to be dependent on the calculator. We don't want to use the calculator as a crutch. But in a problem like this where, okay, I mean, I could come over here and do, 330 times 0.075, but that's going to take quite a bit of time. I don't want to use the calculator as a crutch because I'm unable to do this, but I use it as a tool. I say, okay, I could do it longhand. That's going to take a lot of time. Is that the most efficient use of my time when I'm trying to learn algebra to work through this arithmetic step by hand? Probably not. So I'll come over here to my calculator, 0.075 times, and then 330. Of course, we don't need a graphing calculator to do something like this, but we'll use the graphing calculator more later on. And I see x equals 24.75, and I want to remember that unit of dollars. So what number is 7.5% of $330? $24.75. I could imagine even having a word problem that would give rise to something like this. The tax rate in an area is, the sales tax rate in an area is 7.5%. You are going to buy an item with a stated price of $330. How much sales tax would there be on that item? And there you go, $24.75. So we can imagine this arising from even, a more contextual word problem where this would be a sensible answer. We could imagine it arising from just a more mathy word problem like this, where there's not as much context. In this case, we have $24.75 in either case. Okay, so the next one, 47, is 20% of what number? So again, I have, yep, question.
We are currently still looking at the calculator.
Oh, you can only see the calculator?
Yes.
Oh, okay. Thank you for letting me know. I meant to share my whole screen. And apparently I only chose the calculator screen. So can you see my whole screen now?
Yes.
Okay. Yeah, thank you for letting me know. Sorry about that. I told you, I don't know what, so some days, or most days, the tech works great. And then some days I just it's just an off day for me with tech. That wasn't, I can't blame Microsoft for that one. Unfortunately, I just picked the wrong option when I picked which screen to share. But yeah, so from the calculator, $24.75. And so that's our answer to that problem. Okay, so the next one, here we have 47 is 20% of what number? So 47 is 20% of what number? We'll call that X. All right, so I have 47 equals 20%. And one thing that I can sometimes do is switch my percent into a decimal right away. I know that doing multiplication and division and so on with percents isn't usually the nicest. So I might just right away switch into a decimal. 20% is 0.2, 0.20, or I can get rid of that trailing zero. Of what number? So times X. Or I see that X equals 47 over 0.2. And for this one, I don't think I'll go to the calculator. I can multiply top and bottom by 10, moving the decimal point on the top and on the bottom to the right one. 400 over 2 is 200, 70 over 2 is 35. And then maybe I can check with my calculator. So 235 times 0.2, that does equal 47. Okay, that's good. So in this case, my calculator acted as a way for me to check my answer. And I confirmed that that's right. 20% of 235 is indeed 47. Okay, so let's work on these problems. So we'll take maybe 2 minutes or so, maybe not 2 minutes, maybe a minute and a half to work on this first one. If you finish this first one early, you can start on the next one. Okay, so again, reading through, what number is 23% of 112? We recognize is and of as those important words. Is corresponding to equals in this case, of to times. And what number, that's what we're looking for. We've identified the thing we're looking for. We'll give it a variable name. We'll call it x. So x equals 23%, or I'll just switch that to 0.23 right away. 0.23 times 112. Over on my calculator, I do 0.23 times 112, and I get that x is 25.76. Is this kind of in the ballpark that I'd expect? Well, I know that 20-ish% of 100-ish is about 20. It shouldn't be a negative number. It shouldn't be bigger than 112. It should be in the ballpark of 20. This seems right. So that's another one of these street math ideas. Is I can get sometimes a rough estimate. I can make an educated guess as to the size of the answer. So about 20, because 20% of 100 is pretty close to 23% of 112. 20% of 100 is about 20, and 25, 26 is in the ballpark of 20. So that seems about right. If I got a negative number, if I got 150, I know that they're wrong. But also if I got like 40 or something, 40 isn't really that close to 20. Now, I mean, that's a little subjective, is 28 close to 20, is 32 close to 20. So, I mean, at some point, we're going to have to make a call one way or the other. It's a little bit fuzzy in terms of logic, but that's something else we can do to help check our answer. Okay, and then I think we're going to end after this one. But 32 is 25% of what number? Let's take 3 minutes to go through this one, come back and discuss it. Okay, so for this one, again, we see is and of representing equals and times. So setting up our equation, 32 is 25% or 0.25 times what number? So we get x equals 32 over 0.25. We can divide that on the calculator to get 128. Sometimes we have a decimal or a percent like 25% or 0.25 that we might recognize as a fraction. 0.25 is just 1/4. So really we're asking 32 is 1/4 of what number? We can just multiply both sides by 4 to get x equals 128. That saves us from doing this kind of decimal division. We might see the answer a little more quickly that way. And then as a quick check, x is say around 100. 25% of 100 is 25. That's around 32. That seems to be in the ballpark of what we're looking for. Or we could check directly what's 25% of 128. And that is 32. So that's exactly what I wanted. Okay, are there any questions on anything we talked about today? So we'll wrap up the last little bit of percent applications next time.